All right, let's quickly talk about the lab on the determination of the solubility product. This is the experiment where we added our lead to our iodide to see whether or not we have a precipitate. We know that if we do not have a precipitate, the concentration of the lead and the iodide are too low. Mathematically, it says that our ratio, our Q, is too small and our Q is less than K. If we find that we have a precipitate, then it tells us that the amount of ions we have, the amount of the lead and the iodide, are great enough to shove this reaction in the left direction. And if we get a precipitate, it tells us that Q is greater than K. So what we tend to do in this lab is find our Q where we do, and the Q where we do not have a precipitate, and find the middle value in between those. And we're going to use that middle value to approximate the KSP, or the K for this reaction. So when Q is less than K, we have no precipitate. When Q is greater than K, we have a precipitate. We remember when we're doing the math on this lab that we have to make sure to do our dilutions. So we take, and everything that's mixed together in any one of the test tubes in here is a total volume of 10 mils. We're interested in the concentration of our lead and of our iodide. So to find their initial concentration, which is what we need, we're going to take the volume starting. So let's just do lead, the starting volume of the lead, and that's going to be our V1, and that's called at 4 mils. The original concentration of our lead is 0.010 molar, so M1 is 0.010 molar. Our final volume is 10 mils. And so if we use our dilution equation, V1 M1 is equal to V2 M2, we can solve for the concentration of the lead when everything is mixed into that test tube. When we do, we get these values right here. And we can use these to calculate our Q. Remember, Q here is our reaction quotient, and it is the initial ratios of the concentration. Remember, we have to raise them to their stoichiometric coefficient. So here, if we have the reaction of lead iodide as a solid going into lead aqueous plus 2 iodides, our Q for this is going to equal the concentration of lead, which is what we just calculated doing that 10 mil dilution, multiplied by that concentration of the iodide, also having to look at that 10 milliliter dilution. And when we do this, back to chapter 13, or our equilibrium chapter, we know that we have to raise our concentrations to our stoichiometric coefficients. So we're going to square the concentration here of the iodide, which is what goes over here, and that's going to give us this squared value. So what you're going to do on this experiment here is you're going to remember that your volume here at the end is 10 mils. You're going to take the initial values and the initial molarities. They're both 0.010. And you're going to calculate the concentration here of the lead and the iodide in the test tube when we're mixing them together. We know that our Q here is that concentration of our lead multiplied by the concentration of the iodide squared. And with that, we're going to calculate the Q for this. And we're going to take and write down whether or not we have a precipitate, remembering that at the end, when we want to look at our Q values, here Q minimum is without a precipitate. Q maximum is here without a precipitate. Q minimum is with a precipitate, and we're going to approximate in between those. When we have done that, we're going to look at our data, get KSP. When you're doing this next question, you want to calculate the percent error, simply look up the value of KSP. And when you do that, calculate the percent error. It could be very high. KSPs are very temperature sensitive, and we don't know them as well as we'd like. When we're doing this next one, this is going to require an ice chart, and we'll also require that you take a good look at your solubility or other aqueous solutions chapter, and hopefully that will make sense when you get to that part of that chapter.